not in the mood for consciousness right now. Okay. Anyways, the mole fraction is going to be the moles of substance over the total moles. So in this picture that we see right here, we see there are two components to the solution. There's the moles of solute, and then there's the moles of solvent, which is just going to be water. So basically, in order to calculate the mole fraction, we're going to need to divide the moles of solute over the moles of solute plus the moles of water. So the next equation is a modified equation where we're going to multiply each component of the numerator and the denominator by 1000 over the weight. And so just remember that molality is going to equal millimoles over grams. And so when we multiply each component by 1000 over their weight, then we're going to get molality of that specific component. So this equation is just this equation, except it's going to be reduced. So it's going to be molality over molality plus 1000 over the molecular weight of water. And 1000 over the molecular weight of water is just going to reduce down to 55, because 1000 over 18 is just 55. And also remember that the the mole fraction of the solute and the mole fraction of the solvent added together is just going to equal 1. And so if we know one of the mole fractions, then we can get the other mole fraction just by subtracting 1 by that mole fraction. So if in a beaker solution you have 3 moles of sodium chloride and then you had 2 moles of calcium chloride, we wouldn't be able to add those two together because they're completely different substances. But remember that the osmoles is the number of particles that a mole of solute contributes to a solution. So NaCl is going to contribute 2 particles to a solution, while calcium chloride is going to contribute 3 particles to the solution. So if we were to find the osmoles of this entire solution, we would get 6 particles of sodium chloride and then 6 particles of calcium chloride, which would just equal 12 osmoles, or 12 particles. So because all osmolarities add up, they are really important in the preparation of isotonic solutions. Okay, next. Water moves from low to high osmolarity. So right here, if we had a component with 200 milliosmoles and then another compartment with 300 milliosmoles, water is going to flow from A to B because water moves from low to high osmolarity. So completely different substances could have the same osmolarity. So for example, our plasma is mainly salt and it's isotonic, so it's going to have the same osmolarity as 0.9% sodium chloride solution. And we're not even going to talk about normality. So this problem right here, we're going to calculate the osmolarity. And to do that, first we need to calculate the moles of each molecule and then multiply by the number of particles, and that's going to give us what each molecule contributes to the solution in order to get the osmoles of each species. So right here we have 0.4 grams of NaCl. We're going to multiply that by 1000 over the molecular weight of sodium chloride, and it's going to give us basically the millimoles, and then we're going to multiply that by the number of particles that sodium contributes, which is 2, and then that is going to give us the milliosmoles. The milliosmoles in the solution. And then after we do that for each species, the calcium chloride and then the dextrose, we're going to add up all of those numbers and then divide by the milliliters of solution, which is 100, and that's going to give us 0.289. And this is another problem that's kind of similar to it. We're going to be calculating osmolarity, and so they already give us the molarity of each solution, and so all we're going to need to do is multiply by the number of particles that each species contributes to the solution, and then we're going to add all of that up, and that's going to give us the osmolarity. So usually cations and anions do not interact, but of course there are some exceptions. So if we had something like 0.1 molar of hydrochloric acid, we would expect to see a hydrogen ion concentration of 0.1 and then a chloride concentration of 0.1. But usually this is not the case in real solutions, in real situations, because ions are going to interact with each other. So in this picture below here, we see that barium is interacting with chloride ions, and sodium over here is interacting with the sulfate ions, and these interactions are going to reduce the effective concentration. So to calculate the effective concentration, first we're going to need to know the ionic strength, which is the measure of total concentration of ions in solution. And this is only going to be exerted by ionic species, so something like glucose would have an ionic strength of 0 because it's neutral. So here's this equation. Mu is going to be the ionic strength, C1 is the concentration of the species, and then Zi is going to be the charge of the species. So if we had something like a sodium ion, the Zi would equal 1. But remember, to calculate the ionic strength, you're going to need to add up all of the ionic species in the solution. So here is some examples of that. So for 0.01 molar NaCl solution, what we're going to do is add up all the ionic strengths of the species. So right here it's going to be 1/2 times 0.01, which is the concentration of the sodium, and then times 1, which is the charge of sodium, squared, and then plus 0.01 again, which is going to be the the concentration of chloride, and then times -1 squared, which is the charge of the chloride ion. That's going to give us 0.01 molar. And then same thing for the sodium sulfate solution. So this is the clicker question worked out, and I'm probably not going to go over this because it's very self-explanatory, but I guess you can just look at the work and check your own. Right. So another way to describe the effective concentration is the activity. Ideally, gamma would equal 1, because if gamma equals 1, then the activity right here is going to equal the concentration. But of course we know that the effective concentration is actually going to be a lot lower. So to calculate gamma, what we're going to do is we're going to use the charge and then the mu. And of course we can calculate mu with the other equation that we had right here. And yep, I believe that was all. Okay, see you guys next time.